Good morning, students. This is KG Misra, and I have come with the next topic of the video for class 12th for chapter moving charge and magnetism. Okay. In this chapter, today's topic is force between two parallel current carrying conductors. Okay. In the last topic, what was the last topic? Last topic was that when a current carrying conductor is placed in a magnetic field, then it experiences force. Okay, and we have got the expression for the force acting on the current carrying conductor. Now see, when we are placing a current carrying conductor basically in a magnetic field, no, then this is current carrying conductor. Okay, and magnetic field is here. Okay, suppose magnetic field is like this. That means magnetic field is there due to some presence of some other magnet over here. Okay. And that's why this is experiencing a force. Now, if we replace the magnet by another current carrying conductor, because we know that another current carrying conductor will also produce its magnetic field, no? So, similar situation is there, only we are going to replace a magnet with a current carrying conductor. And then what will happen? Obviously, if there are two conductors, suppose we are replacing this magnetic field with a current carrying conductor, then what will happen? Suppose this is conductor 1 and this is conductor 2. So conductor 1 will produce its own magnetic field in this side. If you use the right hand thumb rule like this, see, the fingers are going inside the board. So this side the magnetic field is directed. Okay, we can write as V1. Okay, why? Because this magnetic field has been produced due to the conductor 1. So that's why I'm writing it V1. Now, due to this magnetic field, this conductor will experience some force. Now, in which direction? We can use Fleming's left hand rule. See, direction of magnetic field, it is inside. Direction of current is upward. So, the force will be in this direction. In this way, we can find out the force, that is F2. Why F2? Because it is acting on conductor 2. Okay. Even you can write F21 because it is acting due to conductor 1. Okay. Due to magnetic field produced by conductor 1. Okay. So, now, in the same way, conductor 2 will also produce its magnetic field this side. So, if you are holding like this, conductor 2, then you see your fingers go inside from this side and from this side it is coming out. As it is coming out, so what will happen? Here the magnetic field will be like this towards you. Okay, and let it be V2. Why V2? Because it is produced by conductor 2. Now due to this magnetic field, this conductor will experience force, and in which direction it is going to experience force? Let's see by Fleming's left hand rule. Now this indicates the magnetic field, as I have told you. So magnetic field is towards you. Current it is upward direction. See, yes, magnetic field is towards you, and you can see current is in the upward direction. So force is towards me. Okay, so force F1 is acting in this direction. What do you find from here? These forces, they are attractive or repulsive? Obviously attractive, because see, this force is going to pull this conductor this side. This force is going to pull this conductor this side. So both will approach each other. And when they are approaching, this force is called attractive force. Okay. Now, if the length of the conductor, suppose, is L1, okay, or suppose both conductors of same length and they are very long conductors, then we can get the expression for them. So I will start from here. Do you remember what is the expression for magnetic field due to a current carrying conductor, long conductor or infinite conductor? We have done that, no? That is mu naught I upon 2 pi r. Okay, that we have got already. B is equals to mu naught I upon 2 pi r, where r is the separation between two conductors, or r is the separation of that point. Suppose this is a current carrying conductor, it is carrying current I, and here this space is free space, and you want to find out magnetic field at point P, which is at distance r from this conductor. Then we get this expression. Now suppose this separation is small d, then what will happen? And we want to find out the magnetic field on this conductor produced by conductor 1, and we want magnetic field on this conductor produced by conductor 2. So, at what distance we are finding the magnetic field due to this? At distance d only. So, what we can write? We can write B1 is equals to mu naught I, because both are carrying current I, suppose, or it is carrying I1 and it is carrying I2. I will draw here, okay. Then yes, this magnetic field is produced to this conductor, so its current will be there, okay, mu naught I upon 2 pi d. This is the expression for magnetic field produced by conductor 1. Now, magnetic field produced due to conductor 2 is mu naught I2 upon 2 pi d. Why? Because second conductor is producing, so its current we have to take into consideration, okay, and separation of the point of observation from this conductor is d, and that's why we are taking d, okay. So we have got B1, we have got B2. Now, let us mark this equation 1 and equation 2. Now, when a conductor is placed in a magnetic field, then it experiences force. Now, let us find out the force acting on conductor 1 first. So, F1 will be how much? It is, we know that I means whatever current is flowing in the conductor, okay, that is I1, okay. L, let the length of both the conductors be L. Both have got length L, suppose, both. So, I, L, D, in which magnetic field this first conductor is placed? It is placed in magnetic field B2, okay, and then sin theta. Now, you tell me what is the angle between the magnetic field and the direction of current over here. Magnetic field is towards you, direction of current is upward. So, see, you can see it is a 90 degree, no? No. So, what we can write here? I1 L B2 sin 90, and sin 90 is how much? It is 1. So what we will get? I1 L B2. This is F1, and then let us mark this equation number 3. Okay. Now we need here value of B2, and that we will get from equation 2. Okay. So now let us take put this value from equation 2 in equation 3. So also drop this now. Okay. I think you might have done. Let's move on. From equations 2 and 3. 2 and 3. Let's see what we get. We have to put here value of B2. So we can write F1 is equals to I1 L B2. B2 we have to take the value from here, that is mu naught I2 upon 2 pi d. That's what we get. The expression for force F1, which is acting on conductor 1. We can rearrange it and we can write it like this, mu naught I1 I2 L upon 2 pi d. Okay, and let us mark this equation number 4. So we have got the force acting on conductor 1, okay, due to the magnetic field produced by conductor 2. Okay, this is the expression for that. When they are separated by a distance d, and conductor 1 is carrying current I1 and conductor 2 is carrying current I2, okay, and they have got the same length, that is L, and the medium between them is free space. Okay. Now in the same way, we can go for the force acting on the conductor 2. So what will the force acting on conductor 2? Let's see. F2 will be, again, it is I, which is the current in conductor 2, that is I2. Okay. Then L, length of the conductor, both have got same length, and ILB, magnetic field in which the conductor 2 is placed, and that is magnetic field B1. Okay. And then sin theta. Theta is the angle between direction of magnetic field and current. Direction of magnetic field is inside and current is upward. You can see the angle, it is 90 degree. So what we can get? I2L B1 sin 90. So what we can write? Sin 90 is 1, so we get I2L B1. That is our F2. So we can mark this equation number 5. Okay. And once we have marked this equation number 5, we can put the value of B1 from equation 1. Okay. So now from here we have to put the value of B1 from equation 1. Now see. So derive this. Okay. Done. Very nice. From equations 1 and 5. 1 and 5. What will we get? Let's see what we get. 1, it was the value of B1, that is mu naught I upon 2 pi d, mu naught I1 upon 2 pi d. So we will put that value over here. We'll get F2 is equals to I2 L and then mu naught I1 upon 2 pi d. Okay. So what we'll finally see, it is, we can rearrange it, mu naught I1 I2 L upon 2 pi d, that is our F2, and we can mark it equation number 6. What do you find while looking on question number 4 and 6? Are they similar? Obviously, they are similar. And when they are similar, what do you find? What you can say? You can say that the forces acting on both the conductors are equal in magnitude. Okay. So hence, I am going to remove this part also. 4th I am keeping because it is needed. So you can write from equations 4 and 6. It is clear that F1 is equals to F2. Okay. Clear? Now we can find out the direction of forces by using Fleming's left hand rule. Okay. So when we found the direction of forces using Fleming's left hand rule, already we have done now. So what do you find? Their directions are opposite. So what we can write? This implies that F1 is equals to minus F2. Why? Because of opposite direction. Because of opposite direction. Opposite direction. Okay. Because of opposite direction, F1 is equals to minus F2. What does this indicates? Yes. Yes, obviously F1 and F2 are action reaction pairs. Okay. And they agree with the Newton's third law. Okay. They agree with the Newton's third law. Got it? They are action reaction pairs and they agree with the Newton's third law. Okay. Now, again I should remove, I think you've done. Okay, I'm waiting. Done. Very nice. Okay. So now force acting per unit length. What will the force acting per unit length? For that what we need? Force upon length. So length we can bring this side. So what we are going to have? I am writing F upon L. I am not writing F1, F2 because both are equal. Okay. So here F1 is equals to F2. Let it be F. Okay. Now what we can do? F upon L is how much? We will get mu naught I1 I2 upon 2 pi d. And this is the expression for force acting per unit length of a current carrying conductor. Okay. When two conductors are placed parallel to each other. Okay. Now, what do you feel this force is? It is attractive, but when the direction of current is reversed, this again we can check the direction. So direction of current is upward direction, magnetic field is towards you, so force is in this direction. You can see this is direction of current, this is direction of magnetic field, this is direction of force. So force is in this direction, obviously correct. Let us check this also. Direction of magnetic field, it is inside, direction of current is upward, so force is in this direction. Okay, this is my left hand. Now this force indicates that they are attracting each other. Now suppose I reverse the direction of current, then what will happen? Will the direction of force will remain same or it will change? Let's check. If I am going to make this direction of current opposite, now let's see what will happen. As the direction of current is opposite, so what will happen? This will produce magnetic field here. And which direction? Let's see by writing thumb rule. This side the finger is going inside and that side it is coming out. See, coming out. So this magnetic field direction will change and it will be point towards you. What about this? This magnetic field remains same because the direction of current we have not changed. See, it is coming out only. Okay. Now, on this, the direction of magnetic field is same. Direction of current has changed. So let's find out the direction of force acting on this conductor. Now, this is direction of current, so it is downward direction. Magnetic field is towards you, so you can see force is towards me. Okay. So F1 is acting in this direction. What about this? The direction of current is upward, magnetic field is towards you. So magnetic field is towards you, direction of current is upward. So you can see the force is outward. That means F2 is outward. What do you feel? These forces are going to take them nearer or separate them? Obviously, they are going to increase the separation between them. Thus, we can say this is the repulsive force. Now, so you write 2 points. First point, when the direction of current is same, in two parallel current carrying conductors, then then the force of attraction acts between them. Full stop. Next point, when the direction of current is opposite in two parallel current carrying conductors, then a repulsive force acts between them. Okay, got it? Very good. Okay. See, using this expression, many times it has been asked in the board examination also to define 1 ampere. Okay, 1 ampere. You have to define 1 ampere using this expression. How to do that? See, when you've got two conductors, okay, of equal length, obviously, and they are carrying equal current. Suppose they are carrying equal current, so what we can write? I into I. Okay, not I1. Okay, and they are separated by a unit distance, that okay, maybe 1 meter in SI unit. Then what you get? If this current is also 1 into 1, so you end up getting mu naught upon 2 pi. Now what is the value of mu naught upon 2 pi? Mu naught, you know, it is 4 pi into 10 to the power minus 7 upon this is 2 pi. So pi cancel out. So what you get? 2 into 10 to the power minus 7. So force will be this much Newton per meter. Why? Because force per unit length. So it will be Newton per meter. So according to this we can define this 1 ampere. Start writing. When two parallel conductors of equal length carrying equal current separated by unit distance, comma, such that force of interaction between them is 2 into 10 to the power minus 7 Newton per meter, comma, then the current through each conductor is said to be 1 ampere. Then current through each conductor is said to be 1 ampere. This way we can define 1 ampere using this formula. Okay. Let's go for a question. Okay, numerical question. See, this is a question. Actually, it is asked in the board examination. Rectangular loop is there. You can see A, B, C, D. Okay, its length is 25 centimeter and width is 10 centimeter, and it is carrying a current of 15 ampere. You can see this 15 ampere. Now, straight conductor is placed at a distance of 2 centimeter from it, like this, and which is carrying a current of 25 ampere. But my dear children, in question, the direction of current in the straight conductor is not given. It may be along the direction of current of this AB, or it may be in the opposite direction. We don't know that exactly. Okay. So let us take that it is carrying current in the same direction first. Okay. And then after calculating the value, we will write at the last, if the direction of current is same in the wrong conductor as that of AB, then it will be attractive force. If it is opposite, then it will be a repulsive force. Okay. That we can write at the last. And let us name this conductor as X and Y. Okay, long conductor we have named as X and Y. Now we need to find out the force. Before going to that, just see, if this conductor is carrying current in this direction, so its magnetic field will be in upward direction this side. So magnetic field obviously will be in the upward direction like this. Here also it's like this, here will be like this, and here also it will be like this. Okay. So this is direction of magnetic field. And now we can find out, see, if you want to find out direction of force on this, what you will get? See, both the conductors of same length and they are same distance from this conductor. Okay, same length means you have to find the distance from the center of this conductor to this. That you will get. See, this is of 10 centimeters, so half is 5 centimeter plus 2, 7 centimeter is the distance. Here also distance is 7 centimeter. Okay. So what will happen? The equal force will be acting on both of them. Now it's time to get the direction of force on both of them. See, we are going to use the Fleming's left hand rule. Okay, using Fleming's left hand rule, see, the direction of magnetic field is towards you. Okay, direction of current is downward, so force is towards me. Okay, so force acting on this, let it be F1, and that is in this direction. What about direction of force on this? The direction of current is upward. Direction of magnetic field is towards you, so force is, you can see, this side. So same as I have told you, same force will be acting, so it is acting same force but equal and opposite. And when the forces are equal and opposite, then what you find? Net force on the loop in the horizontal direction will become 0. Okay, so what we can write? In horizontal direction, equal and opposite forces are acting along same line. Okay, thus F net equal to how much? It is F1 minus F2, and that is 0. So in horizontal direction, net force is 0 on the loop. Okay, now let's go for the vertical direction for AB and CD. Now for AB, the direction of force we can find it out. The direction of magnetic field is this one, towards you. Direction of current is towards that, so force is downward. So we can see this force is downward. Let this force will be F2. What about this? See, direction of magnetic field, it is towards you. Direction of current is this side, so force is upward direction. Force is upward direction, let it be F3. Why I am taking F2 and F3 in this case? Because see, their separation from this wire is different. Okay, and you know, if the separation is different, then force is going to be different. Let us find out the value of F2 and F3. So F2, we know that very well. What is the expression? Mu naught. Let it be I1. Okay, let it be I1. Let it be I2. So we can write I1, I2. Okay, into mu naught I1, I2 into length. Let the length is L. Okay, length of AB or CD we are talking about. Okay, so this length, that is 25 centimeter. This is equals to L. So L into upon 2 pi r, that is 2 pi r is the separation between them. Now what is separation between these? That is 2 centimeter. Okay, separation is 2 centimeters, so we can write 2 into 10 raised to the power minus 2, because in centimeters, so we have to convert into meters. Now what we will get? See, mu naught is up how much? It is 4 pi into 10 raised to the power minus 7. I1 is how much? It is 15 ampere. I2 it is how much? 25 ampere. Length is how much? Length is 25 centimeters, so we can write 25 into 10 raised to the power minus 2. Okay. Now here denominator we have got 2 pi into 2 into 10 raised to the power minus 2. Okay. Now this 10 raised to the power minus 2, 10 raised to the power minus 2 cancels out. This pi we can cancel. We can cancel this 4 by 2. Okay. Now this one, another 2 is left, so we can cancel this 2 also. So what we have got, see, 15 into 25 into 25. Okay. So 25 into 25 is 625, we know that. 625 into 15. So let us do the calculation part. Here we got 625 into 15 into 10 raised to the power minus 7. That's what we have got. This 1, 2, 3 and this 4. Only 4 terms are left. So 15's 5 here. 75. We got 5. 7 is carry. 15 to 30. 30 plus 7. 37. So 3 is carry. 15 6 here. 90. 90 and 3 is carry. So 93. Okay. Into 10 raised to the power minus 7. So if you want to write into decimals proper in the form of scientific notation, then decimal is here at the back side. We have to bring it 1, 2, 3 places. As we will bring 3 places front, this power, negative power will decrease. So we can write 9.375, okay, into 10 raised to the power minus 3 decreases, so minus 4 Newton. That is the force acting. That is 9.375 into 10 power minus 4 Newton. Okay. Now we can go to the second part, that is to find the value of F3. Okay. For F3 again we have to write the same formula, that is mu naught I1 I2, okay, into length of the conductor, that is L, upon 2 pi distance. What is distance from here to here? See, from here to here it is 2 centimeter, and this is how much? 10 centimeter. So total distance is 12 centimeter. So we can write 12 into 10 raised to the power minus 2. Why minus 2? 10 raised to the minus 2. 10 raised to the minus 2 to convert into from centimeter to meter. Okay. We can put the values. It is 4 pi into 10 raised to the power minus 7. Okay. I1 is how much? It is 15. I2 it is 25. Length is how much? Length is again it is 25 centimeters. So we can write 25 into 10 raised to the power minus 2. Why minus 2 again? To convert into meter. Okay. I'm just going to rub this. 2 pi into it is 12 into 10 raised to the power minus 2. This 10 raised to the power minus 2 again cancels out. Pi cancels out. 2 2 are 4 and 2 6 are 12. Okay. Now we can cancel even more. 3 2 are 6 and 3 5 are 15. Okay. So we got here 5. We have got here 2. Now what we are left with, you can check it from here. It is 25 into 25 is 625, and again 5 is there. In denominator we have got 2. Here what else we have got? 10 raised to the power minus 7. Okay. Now we can go for more simplification. So 5 5 are 25. So 5 is there and 5 2 is carry. 5 2 are 10. 10 plus 2 is 12. So 1 is carry. Now 5 6 are 30 and 1 31. This upon 2 into 10 raised to the power minus 7. We have to divide it by 2. So 2 1 are 2. 1 is left 11. So 2 5 are 10. Again 1 is left. So 12. 2 6 are 12. Okay. 5 is there. 2 2 are 4. Okay. 1 is left. So after decimal you will get 0. It will become 10. So 2 5 are 10 into 10 raised to the power minus 7 Newton. Or we can write into scientific notation that we can bring decimal from here to here. So 1 place and 2 place and 3 place. So it will jump 3 places. So we will get 1.5625 into 10 raised to the power. 3 places reduced, so minus 4 Newton. This is the force acting F3. Okay, force F3 is acting on the conductor. We can say CD. Okay. So we got the force acting on conductor CD, and we have got the force acting on conductor AB, that is F2. Okay. Now see, these forces are acting in opposite direction. So we have to find the difference. Now you can see which force is more. Obviously the conductor nearer to this longer conductor will experience more force. So you can see F2 is more than F3 because both have got same 10 raised to the power, that is 10 to the power minus 4, and value is more, 9 point something and 1 point something, okay, that is more. So resultant force will be acting along F2 only, okay. So we can get the net force now. I'm going to rub this diagram because it is not needed anymore. Okay. So now I can find out the net force. Thus, the net force acting on the loop is F is equals to, we can write F2 minus F3, and F2 is how much? That is 9.375 into 10 to the power minus 4 minus 1 point, okay, minus 1.5625 into 10 to the power minus 4. That is there, and we can write here Newton, the unit. Okay. Now what you will find? How to just we can separate this. 10 to the power minus 4 is common. We have to separate the numbers only. So here we got 1, 2, 3 digits after the decimal. Here we got 1, 2, 3, 4 digits. So we can write here 0. Okay. So 0 minus 5 we cannot do. So we will take one carry from here. 10. 10 minus 5 is 5. What is left here after taking carry? 4. So 4 minus 2 is 2. Now it is 7. 7 minus 6 is 1. Okay. 3 minus 5. We cannot subtract 5 from 3. So we have to take carry 13. 13 minus 5. 13 minus 5 means 8. 8. Okay. Now how much is left? 8 is left because one carry we have taken already. So 8 minus 1, that is, that's 7. So we are getting 7 minus 8, 1, 10 to the power minus 4 Newton. This much force is acting. Okay. And in which direction it is acting? Here we will write the direction. If long conductor carries current, okay, just I think grab this, okay, or you can write, okay, start writing from after this. If the long conductor carries current along the direction of current through AB, then the net force on the loop will be towards the long conductor. Full stop. If the direction of current in the long conductor is opposite to the direction of current in conductor AB, comma, then the force will be repulsive and net force on the loop will be acting away from the long conductor. Okay. I mean to say this. I think you have done this. Okay. What I mean to say, see, if this is the loop, okay, and you know very well, loop A, B, C, D was there, and just carrying current like this. And this is long conductor. If both are carrying current in the same direction, then the force will be attractive and it will be acting in this direction. Okay. Towards this net force. Now, if the direction of current in the long conductor is opposite, it's like this, then what you will find? You will find that net force is acting away from it because it is repulsive force. Obviously, this will also experience force, but in question we have asked about the force acting on the loop only. Okay. So this force will try to take away from this state a long conductor. Okay, carrying current. Got it? Okay. students, for watching this. I hope all of you are well and fine and you're studying, devoting your time to your studies for your betterment. Okay, you can convert this hard time of this pandemic into opportunity for yourself, because you've got lots of time to study and you can excel in the future. God bless you all. Thank you.